The only big difference in these and the financial problems is that the time doesn't have to be in years, and you're not dealing with dollars. In this case, on the very first problem, we're dealing with a bacteria colony. Okay, so a colony of bacteria grows according to the law of uninhibited growth. That just means it's exponential. That's all that means. And it's modeled by this function. N of t is equal to 90 e to the 0.06 t. So this is like the PERT formula. It's exactly the same formula. It's just, it's talking about bacteria instead of money. That is the only difference. It says where N is the measure in grams and T is time, and time is in days for this problem. So it is exactly the PERT formula. The difference is we're dealing with bacteria, grams, instead of dollars and cents. And instead of time being in years, time's in days. That time is going to change from problem to problem. So in these problems, time may be in days for one problem, and the next problem would be in hours. So it's going to change from problem to problem. And you don't have to worry about converting or anything like that because, I mean, the equation is going to work for that. So several parts here. The first part says determine the initial amount of bacteria. Okay, so what is the initial amount here? That means the amount you're starting with on that. What would that be? Think about your PERT formula. Where was the starting amount of money? It's right there in the beginning, the P in the beginning of the problem. So it's going to be 90 here. So N of 0 equals 90 grams. If you plug the 0 into the problem, you're going to still get 90 out of that because this e to the 0 power is going to be 1 times 90 is 90. So that number in front there is still it's like the principal amount of the money. It's the original amount. It's what you're starting with. So 90 grams of bacteria is what we're starting with. The growth rate. So growth rate, what's the rate? Well, where was the rate in the PERT formula? It was up there in the exponent. What is that as a percentage? 6%. 6%. And since our time is in days, per day. That's what that is, okay? It says graph that with the graphing utility. So we're going to graph it on the calculator. So that's going to help us to be able to use that to do a few things. So I'm going to clear out some of this mess I was doing yesterday. And I'm going to put 90. To get the E, I'm hitting second natural log. And then 0.06. And then instead of X, instead of T, I'm putting X. Now, I'm going to have to adjust my window so that it fits this situation. All right. So I know my Y value, my initial Y value is 90, and it's a growth rate. So we're going by 6% every year. So I know my window needs to be a lot bigger. My Y maximum needs to be bigger than 90. If we're going by 6% every year or every day, 6% of 90 is going to be what? 10% of 90 would be 9. So it's somewhere less than 9. So somewhere around 6, 5 or between 5 and 6. So I'm gonna grow by 6% every day. So I'm gonna set my Y maximum to be like 150. Or that's I'm looking down here at later questions. It says when will the population reach 250? I'm actually going to set my Y max to 300. Whoop, not 3,000, 300. Okay, and then hit graph. And we should see an exponential growth there. I'm going to set my window on my X max. It says, one of the problem asks for 7 days. I'm going to set it to about 15 days. That'd be 2 weeks worth of a little bit more than 2 weeks. And I just see a little bit more of the curve happening there. Is all I'm doing. So I'm just adjusting my window so that I can see the picture a little bit better and know what's going on. So I've graphed it on the calculator. It says, what's the population after 7 days? So to find the population after 7 days, so C, we did on the calc. D part, it says, what's the population after 7 days? So where's the 7 go in the problem? Yeah, the X. So I'm plugging in 7. I can do that manually and work that out, or because I've done that graph, I can go to my calculator and I can hit trace 7, and it's going to give me the amount of bacteria I have after 7 days. So trace 7. After you graphed it, trace and plug in the X value you need for that. So I got 136.98. I'm going to go 2 decimal places there. Grams. 136.98 grams. And then E part says, how long will it take for the population to reach 250 grams? So this is where I'm going to go underneath there. I'm going to do the algebra for this, and then I'm going to show you how you can use the calculator to help you too out of that. So if I want it to reach 250 grams, so that's going to be my end result. That's going to be like in the financial problems, that's going to be my account worth at the end. All right, so I'm going to set the problem equal to 250. And I'm trying to find out what T is. So this is a problem like Maddie asked about at the beginning of class today. So we're trying to solve for time. So how do I solve that equation? Yeah, divide by the 90. That'd be a great first step. The zeros, I got 25 over 9. I know that doesn't go evenly. I'm just going to leave it as a fraction for now. Now what do I do? Yeah, that's right, because that's going to cancel out my E on the right-hand side. So I'm taking the natural log of 25 over 9, and then the natural log of E to the 0.06t. And that natural log is going to cancel out the E. So I've got just natural log of 25 over 9 is equal to 0.06t. Now I'm one step away from getting my solution. All I got to do is what? Yeah. That's going to give me my time. And so natural log 25 divided by 9 divided by 0.06. 17.03. Oops. 17.03. Now, what's my unit for time in this problem? Days. 17.03 days. Now, here's how I could also solve that using the calculator. Okay. So I'm going to hit y equals, and then I want my y value, or what the equation is equal to be 250. So I'm going to set 250 as y2. I'm going to hit graph. Now, here's where I've got to adjust my window a little bit more. I need to be able to see that this is the graph of my exponential. This is my 250 grams of bacteria. I need to see where they're crossing. So I need to adjust my window a little bit. It's a little further out here. So I'm going to hit window, and my X max, I'm going to put it out to like 20. Yeah, and it showed it. Yeah, that's so you just got to monitor and adjust as you go along there. If you can't see them crossing, then you've got to adjust your window to where you can see them crossing, because that's going to allow us then to use the intersect tool on our calculator to solve that instead of having to manually solve it. So I can hit, once I've got both of those graphed, I'm going to hit second trace. And if I pick option 5, that's going to help me find the intersection of those two graphs. So option 5. And then all I got to do is hit enter 3 times. Enter, enter, enter. That X value should look very familiar. 17.027, that rounds to 17.03. That's the same answer I found when I worked it out manually. The Y value of 250. So that's where they're crossing. That is the days that it took for it to get to 250 grams out of that. So using the calculator to solve there is absolutely legal. You can do that. That is absolutely a great way to get an answer there. We can do it manually, but this is also a way of solving it. Okay, so Now, let's look at F part of this, where it says, how long, what is the doubling time? All right, so if we're doubling this, what are we setting it equal to? 180. So I can either solve that the way we did over here on the left, where I divide by 90, get 2, and then take the natural log, and then divide by 0.06. I can do it that way, or on my graph, what do I need to change? Yeah, change that 250 to 180, and then hit graph. So here's the exponential. 180 is going to come in down here. We're looking for where they're crossing. So I can use the second trace. Whoops, wrong button. Second trace, intersect, enter, enter, enter. 11.55 days. If you did it the manual way, you divide by 90, you get 2 equals e to the 0.06 t, and then you would take the natural logs. So natural log of 2 divided by 0.06 equals t. That's the same number. Okay. So nice little thing with the calculator to help us be able to do something a little easier. Okay. So there's an exponential growth model because we're gaining 6% of our bacteria every day. Let's flip over to the next page. So this one is a little bit more difficult because they don't give us the equation to start off with. Okay. So when they tell us that a colony of bacteria increases according to the law of uninhibited growth, what that tells me is that it follows this equation, the PERT formula. That's what they're telling me. The N sub 0 is, I'm just using that instead of P, and N of T instead of A. So it's the PERT formula. This is just the way they note it in this particular section of that. But it's the same math, okay? So if on the A part it says if N is the number of cells and T is time in hours, so that tells us T is time in hours, express N as a function of T. Here we go. That's what that is. Part B is where we start getting some numbers to start trying to figure stuff out. It says if the number of bacteria doubles in 5 hours, okay, find the function that gives the number of cells in the culture. Okay, so B part, so this is A part. B part says it doubles in 5 hours. Do I know how much bacteria I had to begin with? No, but I know it is twice as much as I started with. Do I know the time that it took to double it? 5 hours. So I'm going to put a 5 in the place of T. Notice that I made that 2 times N sub 0. I don't know how much that is, but it's twice as much as I started with. Now I'm going to solve this for R. So this I have to do a little bit of the math to go with this. So I'm going to divide by the N sub 0. That's going to cancel it out. I got 2 is equal to, I forgot my equal sign, equal to e to the 5R. How do I solve that for R? Yeah, that's right. Because the R is up there in the exponent. I want to get it down. So I'm going to take the natural log of 2 equals natural log of e to the 5R. That natural log is going to do what to that e over there? Cancel it out. So I got natural log of 2 equals 5R. And then I'm going to divide by 5 to finish this problem up, or find the rate anyway. So the rate is whatever natural log of 2 is divided by 5. Natural log of 2, parentheses, divided by 5. So I'm going to go, so my rate is 13.86%. I'm going to go 2 decimal places as a percent. So 0.1386 is what I'm going to write in my equation. So my equation, so I got 0.1386. That's the rounded version of that. Okay. Now, my equation, n of t equals n sub 0 e to the 0.1386 t. That is what they're asking for on B. It says write that, find the function that gives the number of cells in the culture. That is the function that gives the number of cells in the culture. We don't know how much we're starting with, but we know we grow at a rate of 13.86 cells per hour, I think is what our time was in. Yeah, time was in hours. That's a lot. That's pretty fast growing. All right, C part. How long will it take for the size of the colony to triple? If we're going to triple it, what are we going to set? N sub 0 e to the 0.1386 t. What do we set that equal to? 3 n sub zeros. The magic thing is the n sub 0 cancels out. You just get 3. E to the 0.1386 t. So it's almost identical to what we did in B part. Now we just got to find out what t is to triple. What do I do? Yeah, natural log. That cancels out the e. So I have the natural log of 3 equals 0.1386 t. Divide by that 0.1386. Natural log of 3, close the parentheses, divided by 0.1386. And that would be, we're going to go 2 decimal places there, so 7.93 hours. To triple. All right, D part. See if we can use our brains a little bit here. How long would it take to double the second time? How long did it take it to double the first time? No, that's how long we took it to triple. How long did it take it to double? Look up here in our problem. It doubles in 5 hours. So if we're going to double again, 10 hours. Yeah, we don't even have to set up a problem to do that. We know if it doubles in 5 hours, it's going to quadruple in 10 hours. Because the bacteria is not changing, it's not morphing into something new. It's just going to continue to grow the same way. So it's going to be 10 hours. So that one's, you could set this up and have 4 n sub 0 equals n sub 0 e to the 0.1386 t. You could set up that problem and solve it. You're still going to get 10 hours. That's what that problem is going to give you for t. Because it doubled in 5 hours, doubling again is going to take another 5 hours, and you're going to get 10 total hours out of that. So pretty neat thing. Okay. All right, so that's exponential growth we've dealt with there. Now, here is an application of exponential decay. So exponential decay is when stuff fades away. So decay happens with everything in other than some of our more substantial elements. Precious metals don't tend to decay as much. They do decay some, but one of the ways that they've come up with how to age certain artifacts is with carbon dating, carbon 14, and how fast it decays. That's something we know. And then we can use, okay, how much carbon 14 is coming off of this particular item, and then we can use that and reverse engineer and find out how old something is. And because we know the half life of carbon 14 is 500 or 5,730 years. And so let's set up this problem here and see what's going on. So we are losing 0.167% of our carbon 14. Excuse me, let's just read the problem. Traces of burned wood along with the ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon 14. So they know this particular type of wood should have had 100, when it was cut, it had 100% of its carbon 14. At that time they found it, it had 1.67% of the original amount for the size of a piece of wood. If the half-life of carbon 14 is 5,730 years, approximately when was the tree cut and burned? Okay, so half-life. Half-life is the key to getting us our decay rate. Okay, we don't know exactly how much carbon 14 we started with, but we know we started with 100% of it. Okay, so for A part, what we're going to do is we're going to set up a problem. We know that the decay problem works the same way as the growth problem. The difference will be that the decay rate will be a negative number. The rate will be a negative instead of a positive if we're going down. That is the only difference. Now, we started with 100% of our carbon 14. And the half-life of carbon 14 means we'll have half of it left after 5,730 years. Okay. So what this is going to give us is the decay rate for carbon 14. Okay. So we're solving this equation for R. Okay. So divide by 1, that doesn't change anything over there. So we got 0.5 is equal to E to the 5,730 R. How do I solve that for R? Take the natural log. Seeing a pattern that's developing here? Seem to be doing the same thing on every problem. So the natural log of 0.5, then E and the natural log cancel out, 5,730 R. We're going to divide by the 5,730. So we're going to find R there. So natural log of 0.5, close the parentheses, divided by 5730. Now, this is a very, very small number, okay? So that number, take a screenshot of that real quick. That number.
Seniors, a reminder about local scholarships. Right now, we still have the McNeil County VFW scholarship available till the 17th, the Eddie Hill to Ash Ag Education till the 24th, Real Church to the 24th, WC and Adelia Ash Ag Education till the 30th. The Enville Community Club is until the 1st of May. You must reside in the Enville area. And then the Lisa Ross Parker also until May 1st. Those applications are all available in guidance to be picked up and returned by those deadlines. So, if you need any help or have any questions,
E -4 means move the decimal place
I need Millie
4 times
Melton
to the
and
left.
Kara Powers and Jackson Grant to report
Well,
to
that's
the
how I
office when
ended
the
up
bell
with the
rings.
3 zeros. So it was behind the 1, so I moved it 1, 2, 3, 4. That's how I ended up there. That's what that means. Okay. So this is my rate. That's a very tiny amount. It's like 0.01% every year out of that. That's our rate. So it says approximately when was the tree cut and burned. So now we've only found our rate. So what we're doing is we're setting up the problem now. We started with, we'll finish this tomorrow.